Hey guys, welcome back to my channel Gamma Die Gamma. So in this video, like I do with most of my videos that are after proofs or derivations, I'm going to apply the formula or the identity, or in this case the generating function that I derived in the last video. So let's get started and I'll give you a motivation why we need that. Okay, so we have to evaluate this infinite series, is infinite sum, call that S. Say we have the sum from n equals 1 to infinity of the nth harmonic number divided by n times 2 to the n. Now if you just slightly rearrange this will become sum from n equals 1 to infinity of nth harmonic number times 1/2 raised to the nth power divided by n. And this actually, what formula does this remind us of that we recently derived? Well, this generating function formula. So we had the sum from n equals 1 to infinity of the nth harmonic number times, say, some argument z to the n was equal to negative natural log of 1 minus z over 1 minus z. Okay, now the challenge here is, in this guy there is an n in the denominator, and how do we generate a stray n in the denominator? What operation or what process do we use? We use integration. So if you just take this guy, take one z outside, so z sum from n equals 1 to infinity of h to the n and nth harmonic and z to the n minus 1. Okay, and then what you do is you integrate from, say, 0 to x dz on basically both sides. Natural log of 1 minus z over 1 minus z dz. And when I do that, I will have sum from n equals 1 to infinity nth harmonic z to the n over n. We still have the z, but now this is evaluated from 0 to x. This integral we can just keep as it is for now. And when you evaluate this guy, you can take the z on that side. So sum from n equals 1 to infinity, you have nth harmonic times x to the n divided by n is just equal to negative 1 over z times integral from 0 to x natural log of 1 minus z over 1 minus z dz. Now okay, we got an acceptable form. Now the thing is, we have a half over here and we have an x, so we can choose x to be 1/2. When I do that, I have sum from n equals 1 to infinity nth harmonic half to the n over n, which just becomes our s, and this is equal to negative 1 over z integral from 0 to half. Well, we need to take the z inside, right, because it's an integral with respect to z. So we have natural log of 1 minus z over z times 1 minus z dz. Since there was a dz, I need to take the z inside, otherwise we were good. Okay, so now the rub is in calculating this integral. Well, looking at the factors in the denominator, we can use partial fraction decomposition to break it down. So we want to write this as a over z plus b over 1 minus z. We want to write this guy, natural log of 1 minus z over z times 1 minus z, as this breakup. Now cross multiplying, and cancelling out the denominator. Forget the natural log for now. Just have a 1 on top and then multiply natural log on both sides. Denominators cancel out. We have 1 is equal to this guy. So now we have z b minus a plus a being equal to 1. So the constant is 1. That means a should be 1, and since b should equal a because coefficient of z was 0, b is also 1. So that means now this guy, our original integral, rather s, can be expressed as negative integral from 0 to half 1 over the first factor z, which was a for a, and then you multiply natural log of 1 minus z later on, minus integral from 0 to half natural log of 1 minus z divided by the second factor 1 minus z dz. Now what you do is, notice the natural log has a great form. You can use the Taylor series now. So if negative sum from k equals 1 to infinity minus 1 the k plus 1 over k, negative z to the k over z integrated from 0 to half dz, fair enough, minus, now the antiderivative of this guy is just simple, right? You can use u substitution or whatever you want, or let me just do that. Let say w equal 1 minus z. So our integral is from say 1 to 1 minus half, which is half, natural log of w divided by w, but dw will now be negative dz. Fair enough? Yeah. And now you can take a minus 1 to the k, this guy and this negative, everything will cancel out to 1. So you have sum from k equals 1 to infinity, 1 over k, integral from 0 to half z to the k minus 1 dz. This minus and this minus will cancel off. We have natural log of w and a w. So again, if you want to use u substitutions, you can. You just have half natural log squared of w evaluated from 1 to half. Now evaluating this integral is easy. All you get is z to the k over k times k, which is k squared, evaluated from 0 to half, plus half natural log squared of half minus half natural log squared of 1, which will be 0. So when you plug half in, sum from k equals 1 to infinity of 1 half to the k over k squared, this is s, along with the half natural log squared of half. Okay, now notice if this is a special function, it's the dilogarithm of 1 half plus half natural log squared of half, and the great thing is we can actually evaluate this dilogarithm of half, and for the purpose of evaluation we can just use the reflection formula for dilogarithms that I've actually proved. So the dilogarithm of z added with the dilogarithm of 1 minus z is actually equal to pi squared over 6 minus natural log of z times natural log of 1 minus z. So if you choose z to be half skillfully, you have dilogarithm of half plus dilogarithm of 1 minus half, which is half, being equal to pi squared over 6 minus natural log of half times natural log of 1 minus half is again a half. We have 2 times the dilogarithm of half is just pi squared over 6 minus, this will become natural log squared of half. Now divide both sides by 2, so you have dilogarithm of half is just pi squared over 12 minus half natural log squared of half. Now you just plug this in our s expression. Instead of this dilogarithm of half, you have pi squared over 12 minus half natural log squared of half plus this other guy, right, that was already there, half natural log squared of half, and these annoying natural log squares go off, so s is just pi squared over 6. Isn't that a really nice result, given all the troubles we did, you know, of using the generating function for harmonic numbers and stuff? Really nice result. And again, the pi comes out because of the dilogarithms out of nowhere, basically. So just to sum up this short video, we defined s as the sum from, say, k equals 1 to infinity of the kth harmonic number. Let's take nth harmonic number divided by n times 2 to the n. We used the generating function and basically used some integration to get the n power down, then used dilogarithms to get pi squared over 6, which means that this is actually equal to the Dirichlet eta of 2, so sum from n equals 1 to infinity minus 1 to the n plus 1 over n squared. So this has the same value as that. That's a really nice result for today. So I guess let's end it here. I hope you enjoyed it. So please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe, keep doing math. Just live long and prosper. And peace out. Signing off.